Being able to do this now will make our lives easier over the next few days. So what do? Well, what we want to do is solve for t. We want to be able to isolate t. We want to get t by itself. And that really just means we need to free it from everything that's making it not by itself. Why is it not by itself now? It's multiplied by something. It's subtracted from something, or something is subtracted from it. It's inside of this e to the power of, and that's perhaps the biggest problem. I want to get it down from there. If your t is trapped in an exponent, how do we get it down? If you fall asleep in class this week, you wake up and everyone's looking at you because they've asked you a question, you should murmur as quickly as you can, take the logarithm. It will be the answer every time. That's how we do these problems. You take a logarithm. Take the logarithm of both sides. In this case, since we're working base e, we'll take the natural logarithm of both sides. The natural log of e to the 3t4 must be the natural log of 1,000. And what's the natural log of e to the power of 3t minus 4? Remember what we said about e? The natural log of e to the x for any x is always equal to x. Natural log and e to the power of cancel each other out. The natural log of e to the 3t minus 4 is simply 3t minus 4, and this is equal to the natural log of 1,000. You will be tempted at this point to punch this into your calculator and find out what the natural log of 1,000 is. If you're desperate to know, I will tell you now. It's a little more than 6.9. It doesn't matter though. It's a number. When we write natural log of 1,000, it's a number. It has an exact value, and it's not a value we're going to get precisely with a calculator. So for now, let's leave it like this. Let's call this the natural log of 1,000. Let's see if we can finish the problem. In fact, if we look back at the problem, we'll see it looks like something that we're good at solving. It looks like the same linear equation we've been solving since junior high school. And I think we'll be able to bring the equation back up shortly. Here we go. If 3t minus 4 is this, and remember to think of this whole thing just as a number, all I have to do is add 4 to both sides. I now have the natural log of 1,000 plus 4. If I divide both sides by t, I get the natural log of 1,000 plus 4 divided by 3. This is a great answer in that it's precisely correct. The natural log of 1,000 does need to be there. If at this point you're desperate for a decimal, you can plug into your calculator. You can take the natural log of 1,000, which is indeed a little more than 6.9. You can add 4, you can divide by 3, and you can get a number which I'm guessing is a little bit less than 3.7. Your calculator will be more precise, but you can approximate it if you want to. I've been promising you for some time now. I will tell you what's so natural about this bizarre number. This number is slightly more than 2.7. Why is this the basis of natural logarithms? There are lots of answers to this. It turns out we can't understand how nuclear power works without natural logarithms. We can't build a musical scale. We can't look at how drugs move through bodies without natural logarithms, but it's hard to see those examples. It's hard to work through the math, and I don't expect you to believe me. So let's instead look at a picture. What I want to do is somehow use the natural logarithm to make a picture, and in fact, I'm going to make a special kind of picture. I'm going to make a spiral. We're going to cheat a little bit. I'm going to do something that I'm not going to teach you until chapter 10 of your book. It's chapter 10 in my book, at least. It's something that comes up in a thing called polar coordinates, but we don't need to know them to do this example. Let's think about trying to make a spiral. Let's look one more time at the piece of paper. I can start at the origin and spiral out. Certainly, that wouldn't be very difficult to do. And you can imagine, in fact, there are lots of ways of doing this. I could have a very tight spiral or a very wide spiral. How can we decide what to do? And let's make this the rule. Let's make the rule that however far I've drawn the line, if that total distance is x, at that moment, my distance to the origin should be the natural log of x. Does this make sense? This will be the one guiding principle of our spiral, that however far we've traveled, the distance to the center, the distance to the starting point, the distance to the origin is always equal to the natural log of that number. In fact, we can look at a prettier picture of this. This is what it looks like if a computer draws it. This is called, wait for it, a logarithmic spiral, for obvious reasons. This is a logarithmic spiral, and I will tell you it's a beautiful and fantastic spiral. I will tell you, in fact, it's natural. It's based on the natural log, and it's natural in a very fundamental way. If you were to go to the beach and find a nautilus shell, nautilus shells are built over several years by the animals that live in them. They take calcium out of the ocean, piece them together bit by bit in an ever-expanding way to make room for their ever-growing bodies. The nautilus shell, if you were to pick it up and saw it in half, looks like this. It's as if the little sea creature knows about logarithms. And it's not just animals that know about this, plants too. There's a kind of Brussels sprout, the Brassica romanesco, which grows in big pieces. Those pieces grow in little pieces, and those pieces grow in smaller pieces yet. And each of these spirals, if you follow them around, it's not quite as obvious here. This is a 3D picture, and the picture is usually two-dimensional. The spiral follows a logarithmic spiral. Nature works with these. But maybe you're not yet convinced. After all, this is truly natural. Shouldn't we find it beyond the world of living things? Well, a few years ago, a satellite over Scotland took a picture of a storm. It was not quite a hurricane. They don't get hurricanes there, but it was some sort of similar northern latitude version of it. And if you scale back the picture to a few hundred miles up, the picture looks like this. Remember, no one told these clouds where to go. The clouds swirl based on winds that come from a lot of places. But if you trace this path, if you were to model this, if you were to put this in a computer, if you were to look at what's happening here, the spaces between the clouds follow once again a logarithmic spiral. Perhaps you'd like one more example. Perhaps you're still not convinced this is going to be good. Perhaps, in fact, you claim if it's truly natural, it shouldn't just be on this planet. It should be everywhere in the universe. Indeed, the whole universe does seem to know about natural logarithms. Approximately 12 million light years to my left is the M51 galaxy. It's a collection of over 100 billion stars. Most of them are like the Sun. Some of them are much larger. It's been there for roughly 8 billion years. And if you point a telescope at it and take a picture, you will see this. Over the last 8 billion years, these hundreds of billions of stars, these planets, these asteroids and comets that make up the galaxy have assembled themselves along lines, along spiral lines that follow once again a logarithmic spiral. The universe knows about logarithms. We must too know about logarithms. This is where we're headed for the next few lectures.